Solar Circle is a nonprofit organization that has contributed to the construction of a certified green primary school for 500 students in Buyuni, Tanzania. Buyuni is an hour drive from Tanzania's largest city, Dar es Salaam, and lies just south of the equator in East Africa, where the sun shines almost 12 hours a day. Solar Circle is now raising funds for a solar power system installation for the Buyuni school and teacher housing facility. This report will provide a recommendation for system component sizes, lifespan, reliability, and local maintenance feasibility for the optimal system, and is meant to guide Solar Circle in their decisions prior to the installation. In the near future, this solar power system configuration can be compared to contractor bids, estimates, and data sheets provided for the Buyuni school installation. The Buyuni school consumes an average of 27.5 kilowatt hours of energy per day and has a peak of 7.5 kilowatts. Based on this energy profile and the results obtained from Homer Pro, a simulation software, a 14 kilowatt solar system installation is recommended with 7.5 kilowatt inverters, 50 kilowatt hour battery bank, and a maximum power point tracking charge controller. If a 14 kilowatt system were installed at the Buyuni school location, this figure shows the estimated monthly electric production in megawatt hours that can be expected throughout the average year. An example system is designed using Solar Edge software, which recommends the best possible placement of the PV panels on the school roof based on solar irradiance, as shown in this figure. For this example system, locally available components are arranged to best fit optimal system results and provide a proper model for the inverter string configuration. An estimated cost for the system amounts to $46,200 without additional considerations of material, transportation, contracted labor, installation costs, or roof racking hardware and wiring. The electrical devices identified at the Buyuni school by the sisters living there were the LED screw-in bulbs, ceiling fans, and a half-horsepower water pump. Counts of these were given to me based on the number in each classroom and office and the amount of time or amount of liters that were pumped daily. Estimated wattages and surge ratings are found in this table that were later used in calculation. Again, for calculation purposes, the amount of hours per day that the LED lights and ceiling fans were used is important, and the amount of time that water is pumped. Component wattages and average daily use were multiplied together to find the kilowatt hours of the school energy profile. These were multiplied by an expansion factor of 1.25 as the occupancy of the school will increase in the coming years. The balance of system layout displays the several components that contribute to the conversion of the sun's irradiance to AC power. Photovoltaic panels will combine into a combiner box that goes to a charge controller and then to a battery bank. A battery monitoring system is optional, although comes with many batteries. The inverter will change the current from DC to AC and additionally charge the battery. A backup diesel generator is available at the school and should be connected at this point in the system. From there, the power should be available for use and connected to the service panel, which will be connected to the Buyuni school AC load. Now we'll do a brief review of different component choices. Lead-acid batteries can have a low capital cost and are the most recyclable option. However, they have a limited life cycle, low energy density, low efficiency, and have toxic chemicals in them. On the other hand, lithium-ion batteries have a high energy density, high efficiency, require low maintenance, and have a long lifespan. However, they do have a very high capital cost and require special charging circuits for protection. There are many different types of lithium-ion batteries. Specific energy and specific power are the energy or power unit per mass of the battery, respectively. This diagram shows pertinent considerations for the Buyuni school, including safety and lifespan of the battery. For this reason, the lithium titanate, lithium iron phosphate, and lithium nickel magnesium cobalt are all valid options. A trade-off for low cost would make lithium titanate the best option, while a concern for specific energy would make lithium nickel magnesium cobalt the best option. There are many choices available for the PV panel chemical composition. This table reviews the efficiency at standard operating conditions, or STC, for various PV module types. Monocrystalline panels are generally recommended as it's seen that they have the highest efficiency at 16.4% for the amorphous silicon hybrid and 13.5% for the regular silicon. The cost of monocrystalline panels has become more affordable in recent years and is the best option for the Buyuni school installation. The Homer Pro microgrid analysis tool was used to provide an optimal system for the Buyuni school's load profile. Optimization is based on the required output, component specifications, life cycle, battery usage and maintenance, and cost. As discussed previously, a 14 kilowatt panel system is recommended. The estimated PV power output is given here as shown on each hour of each day of the year. The yellow areas occur from around 10 a.m. to 2 p.m., at which time the PV panels are generating nearly 13 kilowatts. The suggested battery type is lithium-ion, and the rated capacity is 50 kilowatt hours. As mentioned previously, the capital cost is very high at around $28,000. The autonomy here is listed as 30.6 hours and is defined as the time during which the load can be met with the battery alone without any solar inputs, starting from a fully charged battery state. While an autonomy of 48 hours would be ideal, the high price of lithium-ion batteries at this time makes that amount of autonomy very expensive. In this figure, the percentage of the battery's charge is shown per hour of the day and day of the year. The batteries are charged to nearly 100% from approximately 11 a.m. to 6 p.m. during times of energy production from the PV system. The batteries are then discharged throughout the night and early morning. The inverter specifications are given in this table for an inverter with capacity 7.5 kilowatts. This gives a margin for error and expansion in the school of 10%. The mean output of 1.13 kilowatts meets the average hourly energy needs of the Buyuni school. The output of the inverter is shown here in hours of the day and days of the year. The maximum outputs are seen in red and orange around 6 p.m., at which time there's a maximum draw on the load. At any given time, the prices and available materials in Tanzania may change. An example system installation is given in this section to provide a practical application of the optimal system found with the Homer Optimizer tool. Choices such as panel location, string and battery bank organization, and inverter and charge controller specifications are independent disciplinaries that are selected based on the equipment. The initial specification taken into consideration is the placement of the PV panels on the Buyuni school's roof. The GPS coordinates of the Buyuni school were used and put into Google Maps and allowed for roof sizing simulation in the Solar Edge design software. Given the location, local weather data was used to produce this figure, which shows the solar irradiance profile of the school. The lightest yellow represents a 99% efficiency, while darker crevices and shadows drop to nearly 40%. The Buyuni school is just below the equator, and therefore a higher irradiance on the north-facing roof is intuitive. 40-watt Trina monocrystalline panels are chosen for this example. These are available for purchase in Dar es Salaam at this time and are rated at 19.7% efficiency with a 50-volt open circuit voltage. These solar cells have a low thermal coefficient for higher energy production in hot climates. In order to use string inverters, each string voltage is suggested to stay beneath 500 volts. Therefore, to stay beneath that, each series string for the open circuit voltage of 50 volts will have 9 panels, and 9 panels can be arranged into 4 strings for a 14.4 kilowatt system. These system inverter ratings are sized to accommodate the surge rating at the Buyuni school of 7.5 kilowatts. 2 strings may be connected in parallel into 2 7.2 kilowatt circuits that feed into 2 inverters. In this figure, a model of the system connection of 18 panels per inverter is displayed with the strings' respective colors, purple and blue, corresponding to their inverter. A Schneider Electric Max PowerPoint Transfer 80 amps, 600 volts solar charge controller is chosen for this example system. This charge controller includes max power point tracking, which optimizes the voltage coming from the photovoltaic array. The average rated maximum photovoltaic array open circuit DC voltage should be 600 when using a string inverter in the system. The power grid in Tanzania is a 50 Hz 230 volt system. Therefore, for a 14.4 kilowatt system, the array short circuit current of an optimal charge controller is given as 60.9 amps, and so this controller is rated at 80 amps, which is suitable for a margin with error. MG Energy Systems high energy lithium-ion battery of 24 volts, 300 amp hours, and 7.5 kilowatt hours is a great option that is available in Dar es Salaam at this time. For a 48 volt, 900 amp hour battery system using these batteries, it would require 3 batteries to be in parallel and 2 batteries in series, and therefore 6 batteries in total. Local capital cost of the components discussed in this example system are found in the table here, giving a capital cost of $46,000. For a 25-year lifespan, the replacement equipment cost, operation and maintenance, and subtraction of salvage capabilities give a value of around $71,000. The capital cost of this example system amounts to $3.2 per watt, which is almost the same as the national average of $3 per watt for residential solar installations. Solar Circle organization has been generous enough to contribute to the construction of the Buyuni primary school and is now raising funds for the solar power system. The designed solar power system in this report is sized to supply the school with all of its necessary electricity during the average occupancy throughout the next 25 years. The configuration given in this report can be used as a guide for decision makers at Solar Circle as they begin the installation of their solar power system.